Okay. Hello, everyone. I think we can start. So today we have two lectures this morning on large language models and giga models even. I will do the first lecture on a topic on what can large language model tell us about language. So when you're really free to ask questions. So I assume that you had two lectures on deep learning and machine translation the two days before, so that you basically have knowledge about basic knowledge about deep learning at least. Anyway, ask questions in case it's not clear. Okay, so the question of today is, this morning, is what can large language model tell us about language? And to answer the question, I first asked ChatGPT to tell me what he can do, what he can say about giving me insight on the nature of human language. And as you can see, ChatGPT is very optimistic and self-confident on its capacities to provide insights for better understanding human language. Well, in this talk, I will try to go more in depth about the topic. The thing that I will be interested is whether really, beyond the statement of ChatGPT, whether we can really expect these models to have some knowledge of language. And here is an example of another question I asked ChatGPT. And it's about a grammatical rule in French which is horrible. It's a typical nightmare for the student in France when he learns the grammar of French. It's called the past participle agreement, okay? Here it's the case where there is a past participle agreement with the direct object. And if you ask ChatGPT whether he has some knowledge of such rules, in fact, I was really impressed by the answer. In general, the answer is correct. So he provides you examples. For instance, we have here, oops, sorry, I will use the pointer. So, oops, you have examples of what it is about. So it's a subject, a verb, and there is a direct object. And in fact, the rule in French says that if the direct object is before the verb to have, then there is an agreement between the past participle and the direct object. And in fact, if you look at what ChatGPT says here, it provides the rule. Actually, the rule is really correct in various places. So it tells you that if the direct object is before the verb, then there is an agreement, and then he provides a case-by-case analysis, a case-by-case application of the rule. What is more annoying is that the examples provided by ChatGPT are generally wrong. So he provides the rule, but when he exemplifies the rule, it's wrong. So that's what is in red in the slide here. So for instance, he tells you that in this example, nous avons mangé les pommes rouges. We ate the red apples. He says that pomme is feminine plural. So rouge and manger agree with pomme. But it's plain wrong because the pomme is after the verb. So it doesn't apply the rule at all, in fact. And so that's more or less everywhere the same route. But anyway, what is very impressive is that it has acquired some knowledge of this rule. Of course, it might have acquired such knowledge because he has processed a large database of grammatical text before. But anyway, he has acquired such knowledge. Now, beyond this introduction, I will, in fact, ask several questions. So the first question I would like to ask in this class is how did we get there? So how do we get to ChatGPT like models for natural language processing? And I think it's really interesting to have a slight historical view of the history of the field to understand why we get there. Then I will just provide a small summary of what I understand and what we want to understand in this class about language models. And then I will provide applications of language models to maybe provide insights on the on way to use them for doing linguistic analysis. And the fourth point will be the question about language model and language structure. And as you will see, language structure is very important when you want to study linguistics, and the structure of language is a fundamental aspect of linguistics. And I will try to illustrate how we can figure out whether language model capture actually a language structure or not. So how did we get there? So generally, when we look at the history of the field, it starts in the Cold War. And the context is that in the Cold War, people were interested in translating text from Russian to English, typically. And the question was whether we could do that automatically. And in fact, the first attempts at that time were really lexical, so dictionary-based, where you try to define dictionaries, mapping words from Russian to words into English. And essentially, that's it. And the thing is that, obviously, it didn't work well. And so there are famous examples of aberrations at that time. So for instance, here you have this example, the spirit is willing. It's a very well-known example. Huh? The spirit is willing, but the flesh is weak. So if you do the word-to-word translation from this text in Russian, and then you translate the Russian back to the English, literally, then you get, so that's the example, the vodka is strong, but the meat is rotten. So it shows that, obviously, this kind of approach is too limited to do machine translation, okay? And there are other examples that were famous in the beginning of the field. So the second one is from Barilel. It's from the ALPAC report. And so it's basically, it aims to show that to process natural language, you need more than just lexical knowledge. And in fact, you need more than basic linguistic knowledge. So there is also context, implicit, and common sense knowledge. So the example is Little John was looking for his toy box, finally found it. The box was in the pen. And so in the 1960s, it was an example provided to show that the translation is not obvious. And if you ask DeepL, which is a state-of-the-art machine translation system nowadays, it's still wrong. So if you ask DeepL to translate the box was in the pen, and then he will translate in French, la boîte était dans le stylo. It means that actually DeepL understood that pen was the writing tool, okay? And it's not like a place where you can put, let's say, animals or whatever. So there is the translation is totally meaningless. So what it means is, if you want to translate that correctly, you need to have some knowledge of the world, some knowledge of the context, and this is something really important to achieve these kind of things. So after the first tries and the first attempts, there were also in the 1950s, that's the beginning of the artificial intelligence, but the symbolic artificial intelligence. And so I think it's 1956, which is the critical year where many things happened. So in 1956, you have the Dartmouth Summer School, which is the summer school where all the main people from artificial intelligence met and maybe designed the field. And that's also the year where a guy called Noam Chomsky wrote his first famous paper, which is called The Three Models for the Description of Language. And Chomsky provides a symbolic framework for modeling language, in fact. And he says that you can model language with symbolic systems. And in fact, from 1956 to 1918, the end of the 80s, That's really the start of the golden age of the symbolic artificial intelligence approach. And so, for instance, Chomsky, so in Chomsky, you can, there is this idea that the sentence, such as everyone loves a woman, has a structure. So the word structure will come back. Like a tree structure, and as you can see, you have one there on the slide. The structure basically gathers a noun phrase together, so like every man. There is the love, a woman, which is also a noun phrase. You can gather the love with the woman, and that makes a verb phrase, and the whole thing makes a sentence. So that was the idea. And in fact, there was also the idea that from this structure, you can compute meaning. And so that's not Chomsky. Chomsky had this idea as well, but it has been formalized for computational linguistics from works derived from Richard Montagu's work. And basically, that's the idea of using you can analyze a language such as English, like a formal language, like a programming language, for instance, and you can compute the semantics of the sentence like you would compute the semantics of a computer language, a programming language. Okay? So where did it go? In computational linguistics and in AI, I think one of the main achievements of this symbolic approach was a system called Trudlu. It's a famous system designed by Terry Winograd in the beginning of the 1970s. And in fact, it was the first chatbot, one of the first very effective chatbots. And the chatbot was about chatting with a bot that could where you had this scene with blocks with colors, pyramids, cubes, and things like that. And you could ask the chatbot questions about the scene, so to tell you if there is a red pyramid on top of, let's say, a green block. And you could also ask the system to perform actions on the scene, so to move blocks from place to place, to put blocks inside other ones, and things like that. Okay, and here you have an example of a dialogue that was meant, and you can find still, if you are interested to look at that, you can find demo on the web. So there are videos of the system at the time, and it's quite impressive. In fact, it works pretty well. And why do I talk about that? Because Trudlu was something quite impressive, and it worked well without any statistics. So there was no deep learning at all, nor even machine learning in Trudlu. But it works very well on a closed world. So the world of pyramids, of blocks, and so on is very well defined. So there is very little context that you can model the context and the implicits of this world. It's possible to do that. And so in the story of the field, the question was, well, given that you have a symbolic system such as Trudlu that works very well in a closed world, the question was, could we generalize to a larger world, to an open world? And that's the key problem we faced in the field. That's basically that it doesn't generalize. The symbolic approach doesn't generalize because if you try to write more rules, like grammatical rules or symbolic rules to manage ambiguities, in fact, you need to, when you move to the open world, you need to write so many rules that you cannot cover the full grammar and the full word knowledge either. So you cannot build a database that contains the whole implicits and word knowledge that we use when we speak about language. So here is an illustration of the kind of problems you have. That's for the grammatical part. You have other problems when you try to generalize for the word knowledge as well. But for instance, here you have the example, John eats a salad with a knife, and the second is John eats a salad with tomatoes. And so if you ask a computer the question, with what instrument does John eat a salad? For the first example, it's obvious it's with a knife, at least for human beings, okay? In the second, as you can see, the second example is exactly formally that's the same, except there is a string tomatoes which replace knife. And so for a computer, with what instrument does John eat the salad? For human, it's just absurd to answer tomatoes, okay? But for a computer, there is apparently no a priori knowledge of the fact that tomatoes are not instruments, okay? And so you start, if you want to handle that with a computer, to be able to build some database of lexical database or implicit knowledge database, okay? So in the field of computational linguistics, and this kind of problem was so it has been easily understood that we couldn't expect to build that very large database of world knowledge and things like that. And it has been in the beginning of the 90s to address these ambiguity problems. It was thought that we should use another approach, and this is where machine learning start to rise. And in fact, at that time, the first data sets were created. So one emblematic data set, at least for syntax, is the Pentry Bank, for instance, which is a data set where you have data, so sentence in English from the Wall Street Journal, that were annotated with structure, like trees, that provides the disambiguation. So that these are humans doing that. And so that's a lot of work. So here you have an example, so that's not the Pentry Bank, but typically the guy that annotates is given a sentence, a raw sentence in English, and has to provide the structure. So here, these are the edges, so these are edges representing the dependencies between the words, such as determiner, subject, object, and things like that, okay? So the problem with this approach, so given that you have such data set, you can train machine learning systems to do structure prediction. And so given a sentence, you can train a system to predict the structure, so the tree, okay? But the problem that we have with this approach is that, in fact, the annotation cost is just dramatic. So to annotate data, structured data like that, it requires a lot of time. So the Pentry Bank was years of annotation, and it was the total data set is about 50,000 sentences. Okay, we had for French and other languages such as Chinese, German, other such data set, but the cost of annotation is really dramatic. So for French, there are 20,000 sentences. It took years to do that. And so that's really the problem. It doesn't scale up, and you have another problem that natural language is not IID. So for instance, if you train a system on the Pentry Bank, so that's the Wall Street Journal, it doesn't mean that the topic that you find in the Wall Street Journal is really economic, you know. And if you want to, let's say, parse or process, let's say, a phone conversation or a natural dialogue between people, in fact, the statistics and the lexical statistics that you gather on the Pentry Bank are just practically useless in general, okay? So, so that's the general problem of domain adaptation, but it's a strong limit of these kind of approaches. So what I would like to keep in mind for the remaining of the talk is that we have basically two main problems when we want to model language. So there is modeling the structure, so like the relation between the word, finding which is the subject, which is the object of the verb, things like that. But there is not only the structure, there is also the rest, and the rest is in fact very important as well. This is basically modeling world knowledge and common sense and related issues, okay? Now I will just say a word about the current models and why we are there. In fact, in computational linguistics, there was this trend from symbolic AI, you know, the one I just talked about. But there was another trend inspired by information theory and by language modeling, and where that's typically the trend that has been dominant in machine translation or in automatic speech recognition, where you will see the language as a Markovian. You will model view language as a Markovian process. So basically, you will try to model the probability of sentences using the chain rule of probability, which basically says that you will do a product between the word at some position I in the sentence given the preceding context. And if you are a Markovian, you will say that the preceding context is limited. So you can look, you predict a word I given the 2 previous words or the 3 previous words. So you have a bound on the context. So this is something that works well. But the difficulty that you have when you want to design Markov models, at least in the history of the field, was about counting and, in fact, estimating the probabilities of these conditional probabilities. So when I was a student, there was a lot of literature on finding ways to estimate these probabilities. And I will come in little details about that later. But it was in the 1990s, a very impressive subject. There were plenty of papers and methods for doing that. So there is something to say about this context. And in fact, it's important to realize that the more context you have, the more convincing your model will be. So here is an illustration of what is the impact of the context. So when I use k equals 1, it means that I have no context. So I will generate language by just sampling words from their unigram probability, so without context. And so it's basically an example of generation where I sample the words proportionally to their probability found in training corpora. And as you can see, that's basically random salad. And what you can see is that when I use more context, so k equals 2, it's bigram, so you just estimate the wi given the previous word, you can see that it's slightly better. And when you have 5 k equals 5, you can see that it starts to look like English. It's not totally meaningful English, but it's better, okay? So this is something important because we will see in a few minutes that increasing context is something that is really the current history. So current models are using a very infinite context, in fact, or at least in theory. So to figure out to figure out how we get to the current models, so I think there are 2 key events in the field. So the first one is the massive use of word embeddings. So word embeddings is an old story. It dates back to the 1990s. So that was used already used by people using latent semantic analysis and singular value decomposition methods. But it has been, it became widespread in around 2013, and it's work from Mikolov, basically, that contributed to make them popular. So the contribution in Mikolov is that he scaled up the approach. So if you want to compute embeddings with singular value decomposition or latent semantic analysis, in fact, it's hard to scale up on very large data sets, and Mikolov provided methods for scaling up the word embedding. Okay, so does word embeddings is something that is okay for everyone, or I haven't? Yeah, okay. So what the word embeddings are providing is basically a static dictionary. Okay, So this is the word embedding method will build a dictionary that maps strings, so the words, to the vectors, which is in fact a representation of the compressed representation of their context. But the problem with word embeddings is that it's still insufficient because it conflates in a single string the different meanings of a word. So for instance, if you have a word such as in French, the word avocat may mean lawyer or advocado, okay? And a basic word embedding dictionary, since it's a string to vector dictionary, will conflate the two meanings. You have the same, for instance, in French, the string est, so est, conflates the word east and the third person of the verb to be, so is. So the recurrent language models, in fact, the other strong contribution to the field is again made by Mikolov, and it's the use of recurrent neural network language models. And in fact, what Mikolov showed in, I think it was his thesis around 2011, is that you could again define language models such the one as I showed before, but he could use an unbounded context. So he could, with a neural network, avoid to assume Markovian restrictions. So there is no Markovian hypothesis in the neural networks of Mikolov. So he can estimate the probability of a word I given the full context from the start of the sentence or from the start of the text. So that's a very important difference. So Mikolov, in fact, is able to increase dramatically the context as soon as you use a recurrent neural network language model. So here I try to illustrate very quickly the thing, but in a recurrent neural network language model, if you assume that in gray you have your static word embeddings, you have in fact a memory vector, which is here represented in blue. So if you, for instance, if you want to predict the word here successor given the context before in the sentence, in fact, the recurrent neural network at each time step when you process the sentence keeps in blue a memory and will insert in the memory the current word embedding and update the memory with the current word embedding. So when you have a memory at some time step, so for instance here, and you want to predict the next word, the memory, in fact, contains information about all the content from the beginning of the sentence up to the position. Okay, and so in some sense, the recurrent neural network language models do contain a representation of the full context from the start of the sentence that is used to predict the next word. So we have this effect here that we really have no Markovian hypothesis anymore. And so I told you a few minutes ago that in fact, when historically, when we wanted to estimate conditional probabilities, it was pretty hard to do that. And we had to use limited context of, let's say, like the three words context or 2 words context. And why is it the case? It's because, in fact, the n-grams that you need to count when you estimate these conditional probabilities are zip distributed. And in fact, so you have what it means to be zip distributed. It means that you have very few n-grams that are very frequent, and most of them are not seen in or very infrequent, or even not seen in the corpora. So this is something that you have for bigrams and trigrams. In fact, let's say about 99% of the bigrams or the potential trigrams, if you do the combinatorics for the vocabulary, are not seen at all in corpora. So the estimation problem is really hard. And so it was, if you are interested by the history, you can look at the papers in the 1990s, where we had methods of smoothing and backoff and interpolation in order to estimate these probabilities. Okay? So when we come with the recurrent neural network, it's somehow much more simple conceptually than these methods that we had for estimating the n-grams. Okay? So the current state of the art is not the Mikolov recurrent models anymore. These are transformer models, so these are transformer language models or BERT-like models. You have typically the BERT, Elmo, and Ernie, which are BERT-like models, and OpenAI, GPT-3, GPT-4 are really language models, so they still implement this formula of predicting a word given the preceding context. So that's the same model as before, except that the estimation for the method for computing the conditional probability is much more elaborate. Okay? So what do these transformer models have achieved is to increase even more and to have a even better representation of the context. I will say a word about that in a few minutes. They can be, so that's one of the key aspects of the transformer models. They can be trained on very large data sets, which is not the case. It's possible to train recurrent models on large data sets, but it's much more slow. So transformers are very efficient, and in fact, they are designed to be very efficiently run on GPU-like processors, which is why they can process very large data sets. The thing that is also very important with transformers is that it's also the first outstanding success of unsupervised or self-supervised methods in natural language processing. Because as you can see, these current language models do not need annotations. You remember the Pentry Bank example. Now we can really use raw text, and so it allows us to scale up strongly. And what is interesting is that the current technologies do not really take insights about the whole part of the field which was influenced by linguistics. I will come back in that a few minutes as well. Okay. So how does it work quickly, the transformer? So there are two families of models currently. So there is the BERT-like models. So these are models that are, let's say, playing a game. They are trying to fill the gap. In fact, when you train a BERT-like model, you provide examples such as the latest breakthrough in blah, blah, blah intelligence. And then the model, when training, has to guess the missing word. Okay? So this is called masked language model because we mask some words when training. And the model, when training, has to predict how to fill the masked word. And there is the second family, which is guess the next word family, which is the incarnation is Elmo and the GPT family, where really we are in the traditional context of language modeling at training. So we have a prefix, and the model has to guess the next word, which is missing after the prefix. Okay, so I don't detail all these things, but basically this is like a game that you can play if you like, and it's basically framed as an optimization problem. So what is important? So I told you that there was this context aspect when we explained the evolution of language model from the past to the present time. And so what we had, in fact, is that with recurrent models, even with LSTM and the whole family of recurrent neural language models, is that even with these models, they had difficulties to access items that were far in the past. Okay, when you use LSTMs, it becomes really hard when he has to predict the next word to take into account a word that was very far back in the context. Okay, and so in around 2014, there was this idea of using attention in addition of LSTMs and things like that, in order to be able to access words that were much far back in the history. And so that's really what is the core at the moment in current models. So in both masked language models and autoregressive models such as GPT, there is this attention. So the idea is that when you, so here I will, if you had the machine translation yesterday, here I will really talk about self-attention. So there is no idea of having two source and target sentence. So given a word, you can compute the attention of the surrounding words by basically computing a dot product between the vectors of the two words. And so the attention is basically, so you first start by computing the dot product between some words, for instance, here. This word here. You will compute the dot product between this word and each other word. Okay, so these arrows in black, you can weight them with the dot product. And then we normalize them in such a way that these scores are probabilities. And so you can compute the importance of the context words given the target word. So that's really the principle of attention, okay? And so this is by using these attention scores that you can expect to directly access, to have a high attention score, with an item that is far in the past. Okay, I skip the details of the transformer. It's much more complex than just attention. But I won't detail that in this class, it's too long. Okay? So how these language models such as GPT or BERT-like models are used in most cases. Currently, the thing is to see is that we don't really are interested by their objective, their natural objective, like predicting the next word or filling the gap. So that's the way they are trained. But the way they are used is really because we want to take advantage of their representations. That is, of the word vectors or the vectors that they will build for each word in the sentence. And so these words are contextualized, these vectors are contextualized. And so that's really like the RNN language model vectors. So these are really vectors that capture some aspect of the context. So when you have a transformer model, the vector, by using attention, will be a weighted sum of the vectors of all the word vectors in the sentence, okay? And so the weighted sum is weighted by attention. So it's a way to take advantage of all the context in the sentence. And in fact, what we are interested in at the end is by the transformed vectors or by these, so that's what we call the representation. So in fact, nowadays, most of the time, these large language models are used as functions, mapping the strings, so the word strings, to contextualized vectors. So these are not like the Mikolov vectors, static embedding. So now with transformers, the vectors that we get are taking advantage of the context. Okay, I will continue. Does that make sense? So here is an illustration. So typically, given a large language model, you can train it on a very large amount of text, and then you can use it for downstream tasks. So typically, here is a first example of use. It's a question answering protocol where you have a paragraph, and then we ask a question on something. So what space station supported 3-minute mission in 1973, 1974? And so the system has to find the answer. And so you can design easily with a BERT-like model, for instance. You will process the whole paragraph with the BERT. You get vectors, so the contextualized vectors for every word. And then you can, for instance, train a further model, so that will take as input these contextualized vectors to predict whether the word is part of the answer or not. So typically, the basic squad initial methodology for squad was really about finding the spans where the answer was, and that was it. So this is an example, but there are plenty of other methods for doing question answering, but that's a very basic example. And what is important is that most of the tasks in NLP, so that's the important thing here, most of the tasks in NLP may be framed nowadays with a similar setup. So you can really have this idea that you will first process the text with a transformer, get your contextualized vectors, and use that as input for the classifier or the model that will perform the downstream task. Oops. Sorry, it doesn't go the... I would... oops. Yeah. Wait a second. Okay. So just to give you an idea of the scaling up, the effect that took place in the last years. So the thing is that why we can scale up is basically that we can process all the words of the sentence in parallel. So in a recurrent model, you have the idea that you are sequential. You process the first word, then the second, then the third, and so on and so forth. And in the current models, like transformers, there is no such sequential process. You process the whole word in parallel, and then you transform all the vectors in parallel. So it's actually, this is what explains that we can actually scale up these models very, very efficiently. And as you can see, so BERT was 2018, the publication. We are in 2023, and as you can see, the training size that are used for training models is increasing very impressively because of these computational properties of the transformers. So here you have also a plot that illustrates, given the year, the size that we have for the models, and you can see that it's increasing very impressively for the last years. So just a word on ChatGPT. So ChatGPT is the thing that we hear from the newspapers. And basically, ChatGPT is a language model. It's the same model as we had before. It's a transformer language model that predicts the next word. And the key difference, so we had GPT-3 let's say like 9 months ago. It was still the state of the art, GPT-3. And it was the language model. And so the thing is that ChatGPT is basically applying some additional reinforcement learning to GPT-3. So if you have tried ChatGPT, you can see that the interface is asking you whether you are happy or not with the generated text. And in fact, this is a notation that you are doing when you click on the happy or not, because if you say that the answer is good, it will reinforce for generating such answers. If you are not happy, it will not reinforce. Okay. So this is something that we guess because ChatGPT is unpublished at the moment. And if you are doing research or work with ChatGPT, be careful because you cannot easily replicate. So if you do an experiment one day, it may be the case that the next day the result will be totally different. I tried that a lot, and in fact, the ChatGPT is constantly updated apparently. So for doing science, it's pretty difficult at the moment because it's really hard to replicate. Okay. And currently, so ChatGPT is trying to fix some well-known issues in the transformers and generative transformers. And the main issues that are remaining are hallucinations. And most of the deficiencies are also related to reasoning. So as soon as you ask such models to do like mathematical-like reasoning, like deduction or system of logical deductions or even arithmetics and things like that, in general, when you want it to do reasoning which is multi-op, where there are several steps in the reasoning, it starts to really fail. Okay, but what you have to know is that ChatGPT is not anymore a self-supervised system. There is, in fact, a very important amount of human annotation in ChatGPT given by the people using it. Now I will provide some examples of fine-tuning language models with special interest in linguistics. So the idea when you do fine-tuning generally is first to do a pre-training. So you train your models on a very large data set. And then the fine-tuning is given you have representation, you can train an additional model for predicting the task of interest. So here is a first example for digital humanities that I made with a postdoctoral student, Louis Grobol. So it's about modeling the history of language. And here is an example about the history of French evolution. So in Old French, the word order is subject, verb, and then object. So there is what's called SVO word order. And in Old French, the word order was very different. So there was subject, then object, then verb. But there was also subject, verb, object. And there were, in fact, plenty of other word orders. And so that's one of the key, one of a very important questions in the evolution of French syntax is why this and how this word order actually evolved. So here there are examples here. So the example says that Roland, so that's the son of Charlemagne, will have the other half. So in Old French, it is written as object first. So you have first the object, then the verb, then the subject. And in modern French, it's subject, verb, and object. So the question behind this kind of work is whether we can find ways to annotate data with structure, let's say with trees, in order to study how the syntax of French evolved through time, from the Old French to the modern French. Okay? So we try, in fact, to actually automatically annotate data with this kind of trees, which represent the relations between the words. Okay? In fact, if you think about it, it's pretty hard to annotate Old French manually, because you have no speakers anymore. That's the thing. Huh? And in fact, if you want, you need to find experts. And it's even more time-consuming than annotating modern French, so it's next to impossible. Okay? So there is an interest in parsing automatically, so annotating Old French automatically. And so doing that is also somewhat complex in the sense that this language is not normalized. So at that time, there was no grammar of French. The people were writing the way they wanted. So there is a lot of orthographic variation. In fact, there was no notion of orthography. There are also the thing that people in different areas of the country were speaking differently. So there is a variation, geographic variation. And so it's a language which is pretty hard to process automatically, at least because of this variation. And so here it's an example of the fine-tuning examples of large language models. So we have for French, but you have the same for English. If you want to do that, you can do the same for English as well. We have Bert-like models for French, like they are called Camembert and Flaubert. And in fact, we have a corpora of Old French. So the full corpora of Old French almost is about 55 megabytes. So that's the full text we have for Old French. And in fact, it's really possible to apply this fine-tuning method to actually improve the parsers that we can create for Old French. So here, this is an example that we did. So what these numbers are meaning is basically if you simply use, there is in fact a very small, so about 10,000 sentences of Old French that are annotated. So where you have the sentence in Old French and the syntax tree. And if you train a parser with this basic setup, you get 81 LIS score, which basically means that 80% of the arcs that you predict are correct, okay, with the labels, okay. If you use the large language model, but not a large language model trained on Old French, but on modern French, actually you can transfer and you can get parsers that are becoming much more accurate. So this is the case here. So where we use to encode the Old French, the modern French, or the multilingual models to encode the words and then to fine-tune on the annotations we have for Old French, then we can substantially improve the results we have for parsing Old French. So that's one of the first examples. So what is the time? I try to, I will skip, in fact, this part because I'm too late. Now I would like, oh, sorry. So that's one of the first use of a large language model is actually to fine-tune them and to apply them to some annotation task. Another question that we can ask about large language models is whether they can actually capture structure of language. So they are really not trained to capture structure, but in fact, I would like to show you that they actually capture structure of language to some extent. So again, you can ask ChatGPT to get just an observation about whether he can actually find structure in language. So for instance, here I asked ChatGPT to find the antecedent of an anaphoric pronoun. So we have the question is in bold. So that's the question I asked to ChatGPT. What is the antecedent of E in the sentence after completing blah, 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 blah. So here you have to figure out that the E is here, okay? So he tries to find the antecedent of the E. So there are actually two possible antecedents. So there is either Jelinek or Charles Socket. In fact, as you can see, he's able to, in general, he's pretty good at finding, resolving anaphora, ChatGPT. And he's also able to explain a little bit why he chose Jelinek and not Charles Socket. So that's something important. Another thing that you can ask ChatGPT, whether he captures some structure, is a basic syntax. So if I ask the question, what is the object in the sentence, every time I fire a linguist, the performance of the speech recognizer goes up. That's Jelinek again. In fact, he tells you that he's the linguist, and okay. And he basically, again, he's in general pretty good at finding relation between words. Yes.
Thanks for the nice analysis, but I have a question because I think that there are two differences or two different meanings of what does ChatGPT know about language structure. So it's the effective knowledge, whether it can handle the phenomena correctly, and it is this type of probing where you're like asking it to do some analysis.
Right.
And I really do not want to mix these two because ChatGPT or the large language models can be very well successful in the phenomena, but still all their analysis, as far as I can understand, are purely based on linguistic analysis written in the training data. If you have any comment on that, or if you had any analysis that would distinguish these two things, the performance versus the ability to talk about it, and the ability to talk about it is only mimicked from the data.
Yeah, okay. Thank you for the question. So yes, in fact, I took several ChatGPT examples to illustrate as introductory of the next point. So in the beginning of the talk, I think the past participle rule in French is basically he dumps a grammar that he has read before, more or less, or something like that. Here, I try to find out that's more operational here. And I don't think he has found this kind of example in his training data. But maybe because he could have passed a linguistic exercise where he's asked to, where people are trying to solve this kind of answer. But here I'm not sure that he has found exactly this kind of example in his, but I don't know. In fact, it might be the case, okay? That I don't know. And no, well, maybe. But in the next few slides, I will provide examples where I'm pretty sure that the model has not seen these kind of examples. But yeah, we don't know actually what he has seen before. So, I will skip this one. So the thing is that I would like to ask several questions. I think I will have time to ask maybe the first two. I will ask the question, to which extent do the models actually capture anything similar to the linguistic structure of language, and not with ChatGPT this time, with models that we've trained on our own to try to avoid that kind of effect. And I will also ask a question, to which extent do these models generalize rather than memorize? Okay, so the example I will take again is this example of past participle agreement in French. Why? Because it's interesting in terms of differentiating pattern recognition versus structure inference. So I will contrast the agreement in French between the subject and the verb in the standard case. This example number 1. So that's the cats that Mary likes a lot play in the garden, where it's basically a case of agreement between the subject cats and the verb play. Okay? Between the two, you have a standard relative clause, which provides content on the cats. Okay? So that's standard agreement, subject-verb agreement in French. And you have another example of agreement in French, which is the object past participle agreement, where the example is he likes the cats that Mary has adopted. And in this case, as you can see, the two patterns are very similar. So you have a noun and then a verbal form after, and there is some content in between. Okay? But the structure of the sentence is very different. So in the second example, it's actually the noun, and then there is a relative clause where you have that Mary or que Marie a adopté. And in fact, the relationship there is really, there is a relationship between the past participle and the relative pronoun que or that. And then you have also to find an anaphoric relation between the relative pronoun and the noun cat. Okay? So these are structurally different examples. So in linguistics, the second one involves a transformation or a movement, where in the first case there is nothing like that. And the question that we basically ask here is whether the model is actually making a difference when it predicts the agreement between the two cases. And we will see that it actually does have a very different process for the two examples. Does the basic question make sense? Okay, we have structurally two different patterns, two different cases, but superficially, these are very similar patterns. Here we use actually not a ChatGPT or a very large model, it's a smaller autoregressive model, so a GPT-like model, and an LSTM, but they are trained on just on the Wikipedia. It's a smaller corpus, but it works already well. And we don't, so I didn't talk a lot about the subwords in the current language models, but we use traditional tokens, and we test the results on the Gutenberg literature text. So the basic question is, do language models capture non-superficial structure? And we ask the incremental model, so the GPT-like model, that given a prefix like the cats that Mary likes, to predict the verbal form, okay, like to play or singular or to play plural. The model has the choice only between two cases. So it can actually, we provide either the two possible answers, and he has to rank and to choose between, so that's a binary choice. He has not to choose among all the vocabulary. And in order to study that kind of examples, we classified the examples we use in the test set by level of difficulty. There might be a trivial case of agreement where it's very simple to find the answer, and there are much less trivial cases. And in order to do this ranking, we define the set of heuristics that could provide the solution. So for instance, if I use an heuristic that says that if I agree with the first noun in the sentence, so for instance here, if I pick cat, and I always, so cat is here a plural form, and then I choose a plural form for the verb, okay? And so we define a set of heuristics, so we can agree with the noun closest to the verb, so that's the other form. So here that would be, I always agree with the closest noun to the verbal form, so it's singular, so I would predict singular, okay? And so we define a set of such heuristics, agreement with the token closest to the verb, agreement with the noun before the closest ke, and so on and so forth. So these are heuristics that, in fact, a machine learning model could easily learn. In fact, it doesn't need to learn about French language. It just can learn about simple heuristics. I always pick the first noun. And it has been reported in the literature that sometimes the model are learning this kind of heuristics. So the thing is that if we have many heuristics, so the hypothesis is that if we have many hypotheses that apply to an example, we will consider that the example is easier to predict. Okay? So because there are many simple heuristics that can provide a solution. If we have no heuristics or very low number of heuristics, we assume that the example is harder to predict. So here is an example. So for instance, here in the first example, we have 5 heuristics that apply. So we will consider that the example is pretty easy to predict. And when we have 0 heuristics that apply, we assume that the example is much harder to predict. So what do we get? In fact, if we test that on the test, what we have is that when we have, so the interesting case is the 0 heuristic case. And what we see is that, so what you have in blue is for the subject-verb agreement. In orange, it's for the object past participle agreement. So that's case 1 in my example, that's case 2 in my example. And what you can see is even for the hard examples, transformers are still having a much higher than chance result. So that's about more than 80. So that's about 80 here, accuracy. And for the object past participle, and very high for the subject-verb agreement, whereas LSTM is getting worse for the object past participle agreement. Okay, so we suggest that in fact the incremental transformers or the autoregressive transformer that we use are kind of capturing something more than just random heuristics, simple heuristics. So the second question that we ask is, where is encoded the number? So how does the transformer will actually manage the encoding of the number, the singular or the plural, between the noun and the verb? And here we made experiments to test that. So we actually divided the sentence in 3 parts. So we have the prefix, that is the part of the sentence that occurs before the noun. Okay, the noun here is instance. Then we have the suffix, which is the part of the sentence that occurs after the verb, or the verbal form. And then we have the context, which is the part of the sentence below that occurs between the noun and the actual verb to predict. Okay? And so if we probe the transformer, so we try to make him predict the number of the agreement, so singular or plural, what we can see is that if we probe for the number in the object past participle agreement case, actually when the transformer is on the prefix, he predicts correctly the number at about 60%. Why is that? Because there is a bias in the data. In general, the singular is more frequent in the training data than the plural. So that's the random baseline. What we have is that if we ask to predict for the suffix, we see that the accuracy is is pretty, if it's getting worse than the case where when you are in the context. So when you probe the transformer in the context, it's in general very accurate at predicting the number of the agreement between the noun and the verb, the past participle form. So we have similar patterns for the subject-verb agreement. When you are in context, so between the two words, you have a strong accuracy, and otherwise it's not. So basically, the number is essentially encoded within the context. So we third test whether we can see difference between the prediction made between the two cases of agreement. To do that, we do an intervention on the model, on the transformer. If you look at how an incremental transformer will predict the next verbal form, in fact, it takes into account, naturally, to predict the verb here, the transformer will have access to all the words in the prefix. Okay? But to do the intervention, we can actually remove some elements of the prefix. So we can remove, for instance, the noun for the object past participle agreement. So if you remove the noun, you remove the key cue for predicting the verbal form. So if you remove the noun, it shouldn't work. We can also remove the relative pronoun, which is in principle also key when you do the object past participle agreement, because the relative pronoun is part of the chain of inference to perform in order to retrieve this agreement. We can also remove the immediate context, which in principle doesn't play much role in the past participle agreement in French. Okay? So we can perform interventions. So we prevent the model from looking at these some parts of the sentence at the time where we predict the verbal form, so plural or singular. And so what we can see here on the plots, so for the object past participle agreement, what you can, we cannot read easily. Oops. So what happens? So the blue, so we will look mainly at the most difficult examples, so where we have zero heuristics that apply. The original bar is the case where you don't mask anything. So that's what the best, so the model has access to everything in the past. When you mask the antecedent, so the noun that in principle triggers the agreement, what you observe is that the prediction becomes totally bad, which is normal. So the basic antecedent has disappeared. When you mask the relative pronoun, it's also very bad, which is interesting because we could have just the model having the heuristic finding the antecedent, and that's it. It could be good. But here, if you remove the relative pronoun, which is important for the theory, because but if you remove it, it's getting bad as well. So that's interesting. And if you mask the context, that is the part which is not important for predicting the agreement, as you can see, the results are still good. Okay, so that's really complies. That's if we look at the theory, the transformer as a behavior that fits with the theory. And here, if you look at the subject-verb agreement, so again, we have the original performance. And for the subject-verb agreement, in fact, we don't need a relative pronoun. So that's basically a relation between a subject and the verb, and you don't need to access the relative pronoun. And in that case, what you can see is that when you mask the subject, the performance drops, which is expected. So the trigger for subject-verb agreement has disappeared. But if you mask the relative pronoun, so here in green, as you can see, in that case, where the relative pronoun in theory is not important, the performance is still very good for the transformer. So in contrast with the preceding example. And if you mask the context, here the performance drops. Okay? But here we have something which is somewhat intriguing, because apparently the transformer is building a different inference for the two cases, for the object past participle agreement and the subject-verb agreement. And the main differences are explained by the role of the relative pronoun is very, very different in two cases, and this matches the basic French grammar expectations. Okay. Okay. Oops. So that's something that doesn't say that transformers are actually learning French grammar perfectly, but it's kind of part of a series of intriguing results about them. So there is some suspicion that they might actually capture some grammatical knowledge. I will just, and I'm a bit late, I'm sorry about that. I will just ask you a question, highlight an issue that is important as well for transformers without providing much more details. So what we actually worked on transformers on respect with structure is about disagreement patterns, where you can see that apparently transformers acquire some aspects of the French grammar. But there are also dramatic cases of failures, which are, and one which is very important is related to the memorization versus generalization problem. So one of the very important questions we have for transformers is whether these are models that are actually memorizing their data set in a very efficient way, or whether they are able to provide actual generalizations beyond what they have learned and stored in memory. And so this is an interesting case of study. So the kind of examples that we have here is a case where we will ask a transformer in a sec-to-sec pattern, and there I don't detail the setup, to predict semantics of the sentence. And that's basically the Cox data set the Cox task designed by Kim and Lindsay in 2020. And so you have a sentence such as the hedgehog ate the cake, and you will ask, you don't care about the actual semantics, but it's the task is to predict the semantics of the sentence. Here you have Ava saw a ball in a ball on the table, and again you want the system to predict the semantics. Okay? And the kind of experiments that are underlying here is that you will train your model on sentence. There is a training set which has not the same properties as the generalization set. Okay? And in fact, in the generalization set, you will ask the system to, the transformer, a sec-to-sec model, to predict semantics for examples that he has never seen as is. So these are patterns that he has never seen in the training set. So here it's a pattern where we typically, in the training set, we will see the hedgehog always as a subject, and we want to see whether the model is still able to predict the semantics when the hedgehog is placed as object. Okay? And here, you have in the training set sentences which are structurally simple. So you have Ava saw a ball in a ball on the table. And here in the test generalization set, we will add some more structure. So there is more recursivity. So that's Ava saw a ball in a ball, on the table, on the floor. So there are more recursive patterns. And the question is whether the transformers sec-to-sec are able to generalize to some more recursive patterns or to patterns such as these ones. And in fact, there are impressive negative results there. So for instance, for the recursive patterns, what we have is basically the accuracy on generalization is about 0. So it's not able to, if the transformer has seen a sentence with, let's say, one embedded sentence or one embedded group, and then you add another one at the test, it fails dramatically. So there are very impressive cases of failure. But on other cases, such as the one here, in general, the transformer can succeed. So if you just move the words from position subject to position object, it managed to generalize. But when you do, you try to get structural generalization, so add more complexity in terms of levels of structure in the sentence, the transformer sec-to-sec tends to fail. Okay, Okay, I will stop now. So just to conclude, I think there are two kind of application of large language models for getting more knowledge on language and in linguistics. So the first one is the fine-tuning approach. Okay, but I think there is also very important aspects related to analyze the kind of structure that the models are acquiring. And apparently, they are acquiring more structure than we could expect in the first place. There are also dramatic cases of failure. And so there is all these questions about whether the transformer is learning like a database or is able to draw more inference for more complex and structural linguistic cases. So, okay, I think I'm done for now.
Thank you. There's one thing I was quite interested in because when we are doing the embedding of words in standard like neural network, we get a linear embedding. So there are quite a lot of features that we still have in the embedding. We can do vector analysis and it still gets us some context. So is there any work on that? What happens if we add the contextual embedding? If we are using BERT as an embedding mechanism, are there any relations which are preserved during the process? Is there analysis on top of that?
By the contextual embedding, you mean like the CLS token embedding?
No, I mean like every word, every token gets translated into dense space. We have 1024 or some similar amount of dimensions. And when we do just the embedding, there are things that we can use for like some sort of generalization. So we can do the vector addition, for instance, and it gets us a token which can be interpreted back to some sort of extent. Is this preserved during the process? Because there is this bypassing, so every layer through the attention adds the context, but on the other hand, we are also adding the original vector. Does some of the attributes of this embedding, is it being preserved during the process, or is there any work analyzing this? Because this is super interesting about the language, what the meaning of the embedding actually, and what are the attributes there?
I agree. In fact, I've been in a thesis defense a few weeks ago where I asked the question to the PhD student whether she could know whether some aspect, because she was interested in modifying the static embedding of the words in the first place. And then there was a whole analysis about modifying the static initial embedding, but she had no idea about the process of transformation and how this static embedding is actually modified or kept original. And in fact, I don't know. But I agree, because I asked the question as well. So and I agree that it's a very important issue to find out what is preserved and what is not. Currently, I don't know any empirical work on this kind of issue. Yeah, sorry.
I find this actually quite fascinating because the space where you have the words, it's completely abstract. We have no knowledge about it. The only thing that we have that there is some sort of like algebra in there that can work, but it's no longer linear space after we transform it several times through nonlinearities.
In fact, I hope that in the near future we could expect to get theoretical analysis of what's going on. And in fact, there are several lines of work at the moment that are seeing transformers as dynamical systems. and to study the dynamics of the embedding from, let's say, the static to the top layer. And in some actually, I know that there is theoretical work that explains how there is this evolution, but not for transformers themselves, for simplified models. Because for transformer, we don't get a formal analysis at the moment. I don't know any perfect analysis of transformers. So you can look at the modern field networks, for instance, where they provide and they show that during the iteration you are actually reaching fixed points, and these fixed points are not random ones, so that you can interpret them. So these are papers from the team of IDIAP. So that's Oschreiter and Ramsauer, and there is also papers from Hopfield himself and Krotov, who are actually providing analysis of these transformers as dynamical systems, but they cannot provide analysis for full transformer. They can just provide analysis for models where you have only self-attention that is at work. But the feed-forward network is currently, you have the feed-forward network is currently not included because formally it's more complicated.
Awesome, thank you.
So I have just a technical question about the masking in the last presented experiment. How exactly did you do that?
So you do that at the time, so you keep the full incremental process, the full autoregressive process, and you do the masking when you predict the verbal form only. Okay, so the model has the whole context, and at the moment where you do you predict the verbal form, you prevent the model, so that's a mask. You have the transformer mask, and you add to the mask, you prevent the model to look at some forms.
Couldn't the information from the mask tokens have leaked through in the previous steps to the contextual embeddings of the surrounding tokens? Yeah.
Yes.
Yeah.
Questions?
Hi. The language model captures the knowledge during training, right? So I would see it as a pattern matching problem. So for different types of pattern matching, does it take equal amount of time? For example, as we know, there are simple matching and also difficult matching problem. So the time complexity, is it constant, or if you change? Depend on the.
You mean for attention?
For example, bird. Because for example, we use bird to do some downstream tasks. It uses pattern matching to find the answers, as I would see, like predicting, for example, mask. We mask a word and then we try to predict the word, right? So I would see it as a pattern matching problem. So for pattern matching, normally there are different difficulties of the matching. So I'm just wondering whether it is always taking equal amount of time, or the matching might be different. The time taken to do the matching will be different for different.
I'm sorry, but what do you mean by pattern matching? I mean, there are plenty of methods for doing pattern matching.
Because as I would see the masking, guessing the word, it is a type of pattern matching. As we learn, pattern matching, there are in finite state machine, there are finite state machine, there are regular expression, there are Turing machine.
Yeah.
So I'm just wondering the time complexity for different type of this. Is it constant?
For the masked prediction?
Yes.
I don't know what you actually mean. It's not constant because you have attention. That's the complexity in the transformer it comes from attention, and it's not constant at all. And if you use a finite state machine, it depends. I'm not sure, maybe we can talk about that after, but...
Okay, thank you very much.
In some of the analysis you're doing, trying to probe whether these models know certain linguistic phenomena, particularly things like agreement and so on and so forth, you were looking at entire word forms and asking, like, in this context, does it guess the singular or the plural and this and that? I'm wondering if you should do the analysis at the subword level, at the actual tokens that the model uses, like BPEs or whatever you have. The reason I'm saying that is because it might very well be that by the time you break down these words into subword units, the affixes that decide or modify the gender or the number on a verb or noun or whatever it is, that they are separate tokens, and in some sense it becomes part of the prediction task to predict that token. So you're not really learning grammar, you're just learning to predict a token. And imagine for a moment that cat was broken down into cat followed by S, and play was broken down into play followed by S. It just says that when you have an S in the past, you don't put an S in the future in English, or when you don't have an S, you put an S, and so on and so forth. So it could very well be that what you're reading as grammatical abilities might just be part of the token prediction task. So to that extent, I'm wondering whether this analysis should be done differently. And the other thing I'm wondering about on the other side is that in some sense, when we all learn to speak grammatically, we are doing it kind of like a prediction task. We're deciding for ourselves what form should I use in this situation. And some of it is informed by the past words, some of it is informed by what I'm going to say later, sometimes depending on the language. And so in some sense, it is not surprising that phenomena like choice of singular versus plural can be done well by mask prediction. So I'm wondering if, some of the Tal Linsen exercise you had, where you had the table on the floor, that's a bit more getting into where it's past simple token prediction that you're doing further reasoning. So maybe that's where one should focus to understand to what extent these models are learning language. There was a similar exercise that Smolensky and others did back when Mikolov was at Johns Hopkins and we did the neural language modeling work. They were trying to figure out whether in these sentences which had two nouns, John asked Alice to reconsider something herself versus himself. So the gender of the reflexive pronoun would have to be correct for the gender of the noun and so on and so forth. And they had an interesting finding, which is that even RNNs were able to get all the cases where an example was seen in training, even though the other words were different. And it couldn't get the cases where, like Bob, for example, never appeared in the second position with something, it couldn't get Bob. Although it knew that when Bob was in the first position, it figured out that Bob is masculine, but it wouldn't. So I'm wondering whether there are other tasks like that. So multiple questions. One is, do you want to analyze them at the BP level? Second, do you want to go to higher level phenomena and so on and so forth? Any thoughts on anything?
Yeah, thanks for the comments. Yeah, in fact, it's an example of things that we did. Obviously, we should, actually, we are interested as using formal languages because, so there is for instance, we try to predict. So for the Tan Linsen task, we are really working on it at the moment. And we are also trying to work with formal languages to find out whether the models can learn structure for, let's say, arithmetic expressions and things like that, where also you can figure out whether they can evaluate such expressions as well. But the thing with formal languages is that we are not in a setup which is really characteristic of natural language, because we miss a lot of features like lexical variation and things like that. But we are actually, so there is a need to really add much more experiments to figure out what's in there, of course. And the current main issue is really about these generalization properties that are actually missing And this is quite worrying to see that you know, if you provide, we can get results on, let's say, arithmetic expression of some depth, you know, let's say with 2 operators. And if you move to 3 operators, group. So there are worrying issues. I think there is a lot of experimental work to be done there. Yeah.
A general question, and to start a discussion as well, possibly. So it is easy to prove with examples that the model is failing to generalize and have the capacity, have understanding of some particular linguistic phenomenon, such as the grammatical agreement or what. But on the other hand, it is difficult to document that it has learned that phenomenon in general. So, what is your take on that? When can we claim that the model understands the grammatical agreement between the subject and the verb? What are the criteria? Because humans also make errors in this.
Definitely, yes. In fact, I think we cannot prove anything with this experimental methodology. I would actually I would be more inclined to accept results on this kind of issues with formal language, actually. Because humans actually are doing a lot. That's a typical French grammatical issue where people are wrong most of the time, in fact. No, I think with this kind of, we can just get an idea of what's going on, whether it just provides us an idea of whether the system has some chances to capture the agreement. But we don't know for sure what it captures at all, in fact. Maybe it captures something totally different, a set of heuristics that have nothing to do. And I would be more convinced if we could, for instance, have experiments on with formal languages where we could generate examples on the run and maybe test let's say, an infinite corpus of tests or something like that, you see. Here we just have some basic observations. I think it's more modest than proving anything at the moment.
On a comment that I was listening to your talk, you talked about Jelinek, after whom this workshop is named. He started it, and the Kim and Linzen work actually was done at a JSALT, and Mikolov did some. So what I'm telling everybody in the workshop is in 5 years from now, we are expecting that your papers will be talked about from the work you do this summer. So all the best.